All right, we're almost finished, but we need to talk a little bit about, we talked about the nucleus being made up of neutrons and protons, and those are called nucleons because they're the particles found in the nucleus, okay, and that's where their name comes from. And basically, they are responsible for what we call isotopes, okay? So, for example, normally hydrogen is element number 1, it's 0.0076, maybe another 0 in there, I'm not sure, something like that, on the periodic table. Now, if we look at this number at top, that's the number of protons, so there's 1 proton in hydrogen. Now, to find the neutrons, we would take the atomic mass number, which is the neutrons plus the protons, and we would subtract them. Okay, this is the atomic number up here, which is the number of protons. Okay, if we subtract that, that should give us the number of neutrons. Well, in this case, 1 minus 1 is 0, and there are no neutrons in most hydrogen atoms. And then there would be 1 electron around it, and we know electrons are negative charge, very small particles. Okay, so they don't really add much to the mass. Now, some people mistakenly assume that, oh, this number down here is because of the electrons, but no, it's not enough. It's still too much to be counted for an electron. This is the average atomic mass. We say it's atomic mass for short, but really it should be considered the average atomic mass. Because out of 100 atoms, most of them, say 99 out of 100, are going to be this, and they're going to have a mass of 1, and 1 only, pretty much. Okay, such a small number of the electrons, they're too small to really add up to anything. But basically that. But for every about, say, 1 atom, there may be what we call hydrogen 3. Okay, and this is an isotope of hydrogen. Right? It has 1 proton, just like hydrogen does. And it has 1 electron, but it has 2 neutrons. Okay? So it says, well, but is it still hydrogen? Yes, because the atomic number is what makes it the number it is. Having 1 proton makes a hydrogen atom a hydrogen atom. That's what makes it a hydrogen atom. It makes it act like a hydrogen atom. That's the number 1 thing. So the atomic number is really like the identification number. Okay, if it has 1 proton, it is hydrogen, and its atom will behave like that. What we have here, hydrogen 3, is considered an isotope. Okay, it's still hydrogen, but it has a different mass, and that's basically what an isotope is. It's just another atom that has a different mass. It has extra neutrons usually, okay, or less neutrons, more or less neutrons. And so if 1 out of 100 of them is this, it would have a atomic mass of 3. Okay, so if you took the average, each of these 99 ones times 1 AMU, that would add up to 99 AMUs. And this one, we have 1 that has a mass of 3 AMUs, so plus 3, that makes 102. If we were to divide that by 100, the average would be 1.02. Okay. Now, obviously, if there was 1 hydrogen 3 for every 100, then the average would be higher, it'd be 1.02. So actually, we know this is an even smaller number than this. Okay. It might be 1 in 1,000 or so. Okay. So very few of these hydrogen ions exist. Okay. Whatever the number is closest, 1, that tells you most hydrogens are hydrogen 1 because that's a close number. So the mass is the average. Usually when we talk about the mass, we just round it up or down to the nearest whole number, and that way when we subtract, we'll get the number of neutrons. Okay, so when you see the atomic mass, just automatically round it up or down to the nearest whole number and do that. All right. Now, if we want to name them, like we said, we usually take hydrogen 3, or you might have uranium 238 or something like that. And then the symbol, we would write the mass of it over the atomic number of it next to the symbol. Okay, so that would be how you would write it, just 3 over 1 hydrogen. That tells you that this would be an isotope of hydrogen that has a mass of 3 instead of the number 1. Regular hydrogen would be 1 over 1 next to the H. 1 proton, the atomic mass is 1, has 1 proton, the atomic number, and that's the symbol. All right. And so isotopes most of the time behave just like each other. They're pretty much the same. One of the most famous uses of isotopes are uranium isotopes, and those are the ones we use to make nuclear power, also nuclear bombs and warheads and stuff like that. And so some isotopes are more stable than others and are more likely to break down. Other isotopes are used for dating things. Carbon-13 is an isotope that's used to date the age of relatively recent remains, human remains and stuff like that. Artifacts, I believe, up to 50,000 years old. Something like that. It's fairly reliable up until that. And that's an isotope of carbon. And over time it breaks down, so it can only be used to date things up to a certain time. But those are some other examples of isotopes. And basically that sums it up. So we only had 2 in a short lecture, so that wasn't too bad. All right, we'll see you on Thursday night.